So our next speaker is Shai Revzen from University of Michigan.
I'll be asking my student Vikram, who got smushed with me in this talk, to present the part of this that is his work. But Andy's always a tough act to follow, and usually I also live in terror of what Andy will think of my talk. But this was a great start, because in some sense he's sort of building up to the same conclusion, I think, as we're reaching for a completely different reason. So I'm going to talk about how we get a simple model for multi-legged slipping. And the first reason you might ask is, why should you care? And so here's why you should care. And this is going to rely on geometric mechanics, so I'm going to jump in but not explain any of that part much. So it turns out that mechanics can be written in this rather odd way, which has translation through the group, which is how you move through space, tied to a geometric term, and then some other dynamic equation related to momentum. A biologist should care about this equation because this part, the geometric part, may be a good model, and it's actually pretty easy to estimate in data-driven cases, and biologists actually know that, for example, in low Reynolds number swimming, this in fact dominates everything. So we already know that in biology, though we usually don't like putting the math in there. Engineers should care for a different reason. So with P low dimension and the fact that we have PID control with high authority, we could dictate this variable r, which is the body shape, as a function of time. And if we're really lucky, we can get what is called the principal kinematic case, when the dimension of P is 0. It includes what people normally call kinematics, but it's also broader than that. And in that case, you'll note that there's no time dependence in these equations. All the time dependence is just in r dot. And now we can do our motion planning computed in parallel instead of in sequence. There's nothing to integrate. We can parallelize this on as many cores as we want and get a 100-fold increase in our simulation time. So this could be really spectacular if it happened to be true. And I'm going to try and convince you in the remainder of this talk that it might. But I'll also let Vic talk a little bit about where we see this is somewhat true in biology.
So the work I did was looking at slipping in biological insects. We looked at a highly maneuverable insect, cockroaches, and investigated the slipping here. Here we used a custom-made scripts from MATLAB, from our lab, and we found that these scripts were 20 times faster than commercial software, and they're able to capture the footholds of these cockroaches as they walk across this foam core surface that we constructed. And we found an interesting result. Okay. We found that cockroaches, as they're walking across or running across a foam core surface, slip 1/5 of their total travel distance. Even when they're walking straight, running right or left, 1/5 of their total travel distance is in slipping. The slipping here can be shown by the red tracks. This is when the cockroaches had their legs on the foam core surface, but we're moving backwards. And here is a video of the cockroaches actually slipping. And here you can really see that slipping action when it moves its leg back across that foam core surface. And now we'll show you some slipping that happens in our hexapedal robots that we've constructed.
So another one of my students, Dan, has been working on hexapedal robots. This is a slide actually from his talk in dynamic walking 2 years ago, where we were talking about steering. And you see that pretty similar to what we saw in the cockroaches, there's a lot of slipping going on in the legs. So if nothing else, for someone like me who's working on hexapods, we need to look at what happens when we have a lot of slipping. So I'll take a little aside and say a few words about what geometric mechanics is actually like. Geometric mechanics is really a way of packing in the observation that if we have a Lagrangian which is invariant with respect to a group action, so we have a group, in this case rigid body motions, and we're saying the laws of physics don't depend on where my frame of reference is placed, that implies this sort of equation which says the Lagrangian at a new position with the transformed velocity is the same as the Lagrangian in the original position and velocity. And that inherently defines what's called a vertical subspace, the directions in which you move that are tangent to the group actions. And then in geometric mechanics, one defines another object, which is called a connection, which selects some complementary subspace at every possible state, where that complementary subspace, the only really important thing about it, it has to respect the group action. That is, when you transform from one rigid body position to another, the selection of horizontal subspace must transform with you in a consistent way. And then you can do something that sort of looks like this. And this is really a lovely observation made by Ostrowski and company years ago, that this is a good way to think about locomotion as a bundle. The center of mass position is in the rigid body group. We have body motions that can cycle around in some base space, and closed loops here rise up through the connection to generate a translation in the group. So it's a very, very general formulation, and sort of a bit more formally stated like this. And the equation I showed you guys before is called the reconstruction equation. Now, one of the things on the theoretical end that we recently discovered is my student Matt, who will be here later this weekend, has a poster, not on this though, has been able to show that even if you don't have a system that's perfectly geometric in the sense of geometric mechanics, if you're perturbed away from the geometric case, it turns out you still might not have momentum for a fair range of quickly decaying momentum cases. So if there is enough decay in the system that momentum dies away quickly, it turns out that there still is a geometric mechanics-like case. And so this idea of geometric mechanics might apply a lot more broadly than we realized before. So now let's see about how we can build a simple model that uses this. And the model sort of looks like this. We want a friction-dominated model that's going to be almost geometric. Our inputs are going to be foot motions in the body frame of reference, so egocentric foot motions. We'll also need a little bit of information about leg stiffness and friction coefficients. And what we want as an output is, how is this body going to move through space? Okay, now notice, nowhere here am I saying anything about forces. This is what's cool about this, and also what's weird about this, because I'm not telling you what forces we're generating. I'm just telling you, I have dictated how my limbs will move. What follows, follows. And so we make one assumption that's very egregious, which is why Andy will hate this talk, and that is a non-standard kind of friction model that has something that looks like viscous friction, the mu times v, but also looks like Coulomb friction because it's multiplied by normal force. And we pretend that we have these vertically placed legs that are moving around, and now we're solving for a quasi-static balance. And we're doing that in a slightly tricky way. It basically looks like this. We start out with our foot motions. We detect which feet contact the ground so that the normal force will match gravity. And then we solve. It turns out you can solve explicitly for force balance in x, y, and moment in terms of x velocity, y velocity, and omega. And that whole part looks a lot like a connection, but we still haven't handled what happens with our pitch and roll angles. Those we solve with a nonlinear solver to address the two other moment equations. And so we end up with essentially a quasi-static solution. Momentum isn't building up because there's zero force and moment on the body. So this is essentially solving for a critical velocity. This is, for example, if I did that in air, it would be your critical velocity falling when the friction matches the force of gravity and the net force on your body is zero. But we're reaching critical velocity instantaneously. That's how our model is solving the equations, spits out omega vx vy. And all of this would be complete hogwash except for the fact that we have empirical support that it's not. So let me show you some experimental results. So this is one robot, our big ant. It's a hexapod. We do motion tracking on it. The blue line is actually the experimental data, because in this case, the simulation data, because it compresses time to infinity, what happens until we reach our critical velocity, into an instant, it's actually very high bandwidth. It's very noisy. But you see that the red line is matching that blue line really, really well. And in fact, if we filter it to have about the same spectral properties, so we filter out the high frequency stuff and leave the same frequency content as the experimental data, you get the green line here, which looks even better. So you see pretty good matches in x dot and theta dot for this robot, you see pretty good matches in basically all of the time series for the other hexapod robot we have. And so he said, well, this is too easy. These are all hexapods. They have lots of contacts with the ground. They're big. Let's ask our colleagues for hammer data. So we got some hammer data from Rob Wood's lab. And you see pretty good fits for a jump, for a bound. Trot is horrible. And indeed, when we look a little bit more at trot, y dot matches OK. Theta dot, nothing much is happening in the trot. And we don't exactly understand what's happening in x dot. So what this really comes to show is this really, really naive model that's offensive to me on many ways and probably offensive to a lot of other people is actually pretty good at predicting and captures a big part of the geometric portion of the dynamics. In fact, it does generate a connection-like structure. That's basically my conclusion. That is that geometric mechanics can offer new and simple models for multi-legged locomotion, and that these connection-like models probably apply a lot more broadly than we thought before. I will plug my students' posters. So Dan is here also talking about how we built the big ant robot. My student Brian, who's done a lot of things related to this, has a poster as well. And as I said, Matt will be here later. Other students and colleagues on the slide and funding. Thank you.
So maybe I missed this, but the point that you were setting up is that it's going to be a geometric model, and that you just need to know the geometry of how your legs are moving. You don't need to know the forces involved. But then at the beginning, you were setting up this whole thing about friction and how it's important that you're sliding all over the place. Can you help me? Where did I miss the part that the sort of the stick-slip transition was being accounted for if you don't have sort of force models?
So I am blithely and brutally ignoring stick-slip by not having a standard Coulomb friction model that has static friction and dynamic friction. This is why I highlighted the place where I did utter violence to Coulomb friction. So the answer is there is no stick-slip.
But I thought your geometric model, you didn't have force calculations. You didn't have to calculate the force. Didn't you say that?
So the geometric model has no forces as inputs. To figure out what the geometric constraint is, we're solving for zero wrench on the body. So zero wrench is a Pfaffian constraint. It's a geometric constraint. It has no time in it. So it's geometric in that sense, that however much faster you follow that shape change, that's how much faster you'll actually move. And our data shows that that's pretty true. That is, if you move twice as fast through the shape change, you'll move twice as fast on the ground through almost exactly the same motion, even though there's a lot of slipping going on.
Got it. Maybe.
Well, I'm happy to share the data. Yeah.
Did you look at maybe the relative accelerations of hammer, and were you sort of violating this quasi-static assumption or something?
Actually, what I think is going on in hammer is because of the way our model is built, it will not solve for this equilibrium unless you have 3 points of contact or more. And because hammer is essentially a quadruped, something there is creating these really sharp spikes that are sort of trying to account for the fact that we're not getting contacts that are quite the right structure for our model. As I suspect if we had a hexapedal robot the size of hammer, this would probably work.
This is not a question. I'm going to just try to translate what you said, and then you can, for the benefit of the audience, which is just leaving out the fancy language about geometric mechanics and so on. When something is locomoting, it moves somehow, and it's got what you call egocentric motion, which is you look at the joint angles and so on, or the rotation of the axle of the car, or whatever, and then you take that thing and put it in an environment, and you solve the laws of mechanics, and you get the motion. If you take if you say it's slow enough, then the laws of mechanics are the sum of forces and sum of moments are zero. And then those can only be achieved if the whole motion of the thing has the right thing as a sequence of time. And so basically it's what they call quasi-static dynamics or quasi-static locomotion. You solve the equations of statics at every time, and that gives you motion. And that concept, maybe geometric mechanics and all that language helps you, but I feel like it's I think I understand your talk without using any of that language. But
So-
maybe I'm missing some very deep thing. But I saw Jim Ostrowski talk about this in 1999, and I thought that then, and I think it now.
So I think in essence you're right. I'm making the observation that quasi-static doesn't need to mean slow and doesn't need to mean without slipping.
Okay, so that it works with fast means that the average, the accelerations away from the mean are relatively small, which is what you. So it's not just a matter of reaching terminal velocity; it's a matter of the accelerations within the motion are relatively small.
I think it's a matter of momentum
terminal
effects decaying quickly, which doesn't necessarily mean that the accelerations are small, just that they happen to cancel out momentum.
No, it's not just the overall momentum effects within a cycle. In your terminal velocity, if you did the full dynamics is not quite unlike a person falling through the air. In this complicated motion, the full dynamics is not a steady state thing with no accelerations. So there are always, even when you reach terminal velocity, the remnant accelerations, and you're saying those are relatively small in terms of affecting the net forces and net.
Well, I'm trying to say something more than that, but perhaps we can talk about it later.
Okay.